Hello, my name is Michał Mrozek. I work at Intel, and today I would like to present how at Intel we optimize compute drivers by writing good benchmarks. Okay, let's go ahead. So here is an agenda for today. We will start by explaining why we created compute benchmarks, then we'll go further with framework capabilities. We'll also show what are the current tests. We will also share one success story, and we will finalize with the plans and contribution guidelines to the project. Okay, let's keep going. So why really created this compute benchmark, this test suite? This all boils down to optimizing the drivers. So in order to be competitive, the drivers needs to be highly efficient. And in order to be highly efficient, you need to make sure that the workloads that you run with your drivers execute very efficiently, and there are no bottlenecks in the software stack. But this is quite challenging. Like, there are different types of applications. Those applications measure very different things. You need to carefully understand what given workload measures. And here are like two basic samples. The application on the left measures the time on the host side. So it starts the timer prior to like allocating and executing the workloads, and ends it when it's all done, and then reports a CPU time. While the second application is only profiling the time spent on the GPU itself using the profiling capabilities. So those two workloads are optimized very differently, and you need to focus while optimizing those on completely different things. And you need to carefully understand what given workload does. And most of the time, you don't know this because the workload is closed source. You don't know what it's doing, and you need to assume those things. And even if you know all of this, like you know application in and out, you have the source code, you have full access, then the workloads itself, optimizing the driving using those workloads itself is very challenging because the whole execution may be like very long, and the application may respond like differently to your changes. It may choose completely different code paths when you change something in the driver, and it may uncover completely new problems, completely new things, and the performance would actually degrade, which would be like completely unexpected due to new code path selected in the application itself. So yeah, that's like a problem number one. The applications are complex, and understanding what to optimize and how is very challenging. Another thing that's very important is that those applications consist of like multiple steps. They are huge. And I've noted some steps that each application pretty much does. And as you see here, there is a lot. And if you want to optimize those steps, you may not even see the difference with your application score. Because if a given step that you optimize is only like 1%, even if you remove it completely, the application will only boost like 1%, which is not a lot. And applications, really, the whole workloads, they all measure all those things together, and they provide like one unified score. So it's an output of all those steps combined together. And using those applications, those benchmarks that we already have on the market is very challenging because they measure all of those things. So you need to optimize all of those to really affect the application. And imagine that if all of those steps are pretty low, there is no like obvious outlier, then you need to focus on all of those things to really boost your application. And that is challenging as well and very difficult. So because of that, what we are seeing in the driver development, that really working and using the customer provided workloads and applications is not really efficient in the terms of developers' efficiency. So we are optimizing those applications because we wanted great scores, but using those workloads, those kind of workloads, was not effective, and was very time consuming and was producing a lot of overhead. So this created like a need to create something new, something that would improve the developer efficiency. And that's why we created Compute Benchmark Test Suite. So, and here are like basic principles that those compute benchmarks do. So what we basically created is a test suite for the driver team to allow optimizing the driver using simple and controllable infrastructure. And in this compute benchmarks, we can take those all complicated pieces out of application, and for each of those pieces, create a separate micro benchmark and only measure this one thing in a given test. So if you look at those stones on the right, this is like your whole application. And this whole application consists of multiple smaller stones. So each test in compute micro benchmark is one of those stones. So each test is very simple, is as simple as possible. It just tests one thing and produces a reliable and reproducible result. So every time you run this benchmark, you'll get exactly the same score. And how we do this, I will explain a bit later. We also, in this compute benchmarks, focus to use plain API. We don't use like wrappers. We avoid things like that. We just want to clearly measure the API calls or the scenarios that are of interest to us. And we make sure to do not count any additional overhead that may come from using some kind of wrappers, some kind of helpers, and stuff like that. And because of that, because we use the API, those tests are also a great way to show how the API should be used. We can like literally share a test source and show the proper API usage to multiple people, and that's very beneficial because people are often asking the driver team how to use the API efficiently. And now we have this compute benchmark test suite, which we can utilize to show how the API should be used and what you should reason about, what you should avoid, and what would be beneficial for your application. Another thing that's very important for the compute benchmark is that it's easy to download and build. So you just fetch the repository in the GitHub, and there are no like external dependencies, no third parties apart from the driver required. So you can easily build it and run it. And what we also focus is to have a capability to easily add new test scenarios and easily modify existing ones to make sure that we can move very quickly. The developer efficiency is like a key here. This is a tool to make sure that driver optimizations are easier and much more efficient development wise. Okay, going further. So the compute benchmarks are already available on the open source. We've shipped it a month ago, and they support Linux and Windows operating system. The license permissive is MIT. It runs on like any GPU hardware supporting OpenCL, so this is not like Intel proprietary APIs. It obviously allows vendor extensions and vendor-specific tests, and we have some of those like Intel-specific there. But in many tests, we use just plain OpenCL, so you can run those tests on any architecture that supports OpenCL, and they run and they produce results. So they are also very useful to compare given architectures, especially because those benchmarks are very specific to a given test. So it's very easy to compare one driver to another, one implementation to another, and see how they behave. The full code is in open source, and it's in the GitHubs. And with all of this is all the open source goodness. So it's open to community. Everyone can download it. Everyone can like contribute and enhance this framework. Okay, so this is a bit of a why. Let's see what are the framework capabilities. So the architecture of the framework is that you define a test by specifying what are the test arguments, argument descriptions, what is the test definition, and what are the argument values. And when you specify a test like that, the framework allows you to run this test on a given backend. And you provide an implementation of the given test for a given backend. Today, we have 3 backends, an OpenCL level 0 and SYCL backends. So you can take a test with a given test set of arguments, and you can write your backend implementations And further, you can simply compare the results with different backends. And this was very useful to the driver team. We managed the OpenCL and Level 0 drivers, and we need to make sure that both are equally efficient. So for us, it's a very good tool to simply compare how in a given test scenario OpenCL and Level 0 behaves, and if there are any like differences which needs to be like optimized and cleaned. So each backend receives the same arguments and is capable of running the test. It does it completely differently because of how the backend works. But this allows from the higher level to compare the given scenario between multiple implementations. Okay, so let's see how it's implemented. And this would show the raw source code that we have. So when you add a test, you define an argument, a container for this test having the arguments. So you specify what would be the things that are changing in the test. And those would be arguments that you can permute. Then you define what each argument does. You define what is the definition of this argument in a text manner, and you define how you can override it. So the framework allows you to run each test separately. The framework allows you to run each test with any parameters that you want. There's also a predefined set of arguments that we use to run the test when you run whole test suite. But you can easily extract single test instance and run it with any arguments that you want when you optimize. Here we have a test definition and explanation what the test does. Later, you need to define how those arguments are obtained using the test definition. So you basically translate the permuting parameters to arguments that are defined for a given test. And that's pretty much it. This will result in this test run with those different set of argument values. And this framework will permute all the possibilities to make sure that test checks all of those things. And here is how the sample backend implementation for OpenCL test does. So the goal of this test is to run an NQND range, CL NQND range kernel API and see what's the overhead of this API on the host side. And as you see here, we define a method test result run. It would get those arguments, and this would be common for every backend. So you provide an implementation of this method for every backend, and every backend runs this run command. So first thing, we have this common set of arguments. For each backend implementation, you transmit the argument values to the values that given API understands. So if you are using event, you'll create a CL event here. If you have a workgroup count and workgroup size, this would translate to global work size in your test. And if you have a workgroup size in OpenCL, it will be called local workgroup size. So we are running an empty kernel. What we do every test to make sure that results are reliable and repeatable, we do a warm-up iteration. So think of it like running the tests and what the test will done further one time before to make sure that driver is initialized, all the lazy allocations are done. We want to measure what would happen in the hot path. So what would happen when you run further iterations. That's what's the area of interest here. Of course, warm-up kernel is like optional for you. You don't need to do this, but it greatly improves the stability of the test. And here is the actual benchmark. So we run multiple iterations and we combine scores from each iteration using the statistic class that we have. So for each iteration, we clearly show what's the area of interest by measuring the timer start and timer end. And we measure only the CL NQND range kernel call. We do not measure like how much it took on the GPU. We do not measure how much it took to flash. We just make sure to measure the thing that's the area of interest in a given test. And for each iteration, we collect the timer and we put it to statistic. And this statistic class would later be responsible for generating the output of the test. It would collect all the samples. It would provide multiple metrics. I will show it in the next slide. So you can easily see how your test behaves. Okay, and this is a sample output of this test permuted with all those parameters. So as you see here, we measure the CLNQ and range kernel time. We either enable profiling on the queue, we either use out of order queue, we also return an event or not, and we have different workgroup sizes. So as you see here, there are like very different times reported based on the scenario, and test produces you with a lot of useful information, like what was the maximal time for this operation, what was the minimal time, what was the average time, and what was the median time. And you can utilize all those statistics to see how your driver behaves, how this works in a hot loop, if there are any like outliers. Like here we see that there is some kind of fluctuation, like maximal time is much higher, which may be like analyzed. We can also see that producing an event and profiling heavily increases the NQ and the range kernel time, which shows that profiling have like overhead on the host time of this call. And this provides you a very like clear picture about what are the overheads and what are the overheads associated, and you can like clearly see what's the best average time. If we see here we have like 2 microseconds, which is when we use out of order queue, we do not use profiling, we do not use events. So that's the point where like CLNQ and the range kernel has the less overhead. So as you see here, adding events adds overhead, adding profiling adds overhead, and all those things influence the execution time. And for the driver team, it's like we can easily identify what's expected here and what's not expected, and we can optimize those things. And by using those permutations, we can clearly see the outliers and try to do something with this. So this is a very useful tool. We also have a type of measurement. If you see here that there is a CPU, it means that we check the wall clock time using this CPU infrastructure of timer standard. And we also have capabilities to measure the GPU profiling, like GPU execution time. And we clearly showcase what's the type of measurement. Here we say that this time is in microseconds. Okay. What's very neat about the framework is that when you add tests like that, you structurize them, as I showcased in earlier slides. The framework will automatically, and as a part of your commit, actually, it will generate a documentation. So framework, when you just build it, it creates a documentation and documents what your test does. And because we were required to add explanation about all the arguments and what the test does, you will not be able to compile without this. It creates a very coherent ecosystem in which just by adding a test, you also add the documentation and you clearly define what the test does. And it is very, very useful because having documentation like that creates an environment where external users can easily see what the tests are already written and what can be permuted in those tests and what the test does. And it also shows what backends are implementing the test. In this case, we see that those tests are implemented using L0 backend. So backend is optional. You don't need to provide an implementation for a given test. So you may like write tests that will only make sense with level 0 backend. But you can also write tests that would have multiple backend implementation and check how those behaves in those scenarios. If you want to try it out, that here is like a link for you may see how this documentation look like. And now how we work on those tests within the driver team. So usually what we do, we write a new scenario, we run it, then we use the dump command lines command, which basically, instead of like providing a nice test description, it will provide arguments that you need to pass to a command line to reproduce just this one scenario. So as you see here, when you run this test with this variable, it will provide a command line to reproduce exactly this case. So you can later like run only this test with these parameters, and this will result in only this one test case being run. And now it creates a very, very useful environment because you can easily permute those parameters. You have them directly in the command line. You can very easily optimize the driver here because you can easily control the inputs. The test is minimized. It only does one thing. You can easily modify the driver without the fear of breaking anything or complex applications, and you can quickly see how your driver changes influences the performance. To speed up the things even more, you can add like mark timers, and this will provide you in the output where the timer is actually started and when it ends. So if you add logging to the driver, you will clearly see what's being logged in the hot loop, what is being measured. So you would be able to very quickly identify what portions of your driver stack are being utilized and what needs to be optimized, what happens in the hot loop. This is very important to understand what happens in the hot loop by those clear markers. And if you want to look at outliers, there is a verbose parameter that basically allows you to show all the samples from your test. And as you see here, with the immediate results show that only first iteration was showing the significant increase of time. So that's something that the driver team needs to analyze because this was after a warm-up, yet still the first iteration is substantial. So something is going on even after the warm-up iteration, and the driver can take a look and further optimize this. So this creates a very, very efficient environment to deliver driver optimizations, and we already use this multiple times to work on driver optimizations. It's like this is our main mode of operations right now. We first extract what's important from the client's workload. We create a micro benchmark out of it, and then we use these micro benchmarks to optimize the driver and finally provide an optimization to our customer. So this is how we work on a daily basis right now. And we utilize this framework with a great success. So let's look at what are the current test suite, and I will share the success story about one optimization, how we did it and how it played out. So we have multiple test suites which have different tests with different meaning, with different targets, and checking different things. So we do not only focus on driver overhead. We focus pretty much on every portion of software stack or even the GPU execution that may be important for the application, and pretty much we can write benchmarks covering all those scenarios. There is no limits. We do not only limit to driver, we can measure everything that's important for the application. So the first important benchmark is API overhead benchmarks, where we check whether given API calls, how expensive they are, how long they take, and we can easily use this to check if there are any outliers. So think of it like I was showing, the MQ and range kernel, how much of an overhead this call have on the host side. Then we have a memory benchmark. This benchmark basically checks what is the bandwidth obtained using various transfer calls. Like if you do write buffer, read buffer with different parameters, blocking, non-blocking, maybe the pointer is coming from malloc, maybe the pointer is coming from host allocation. This all makes a difference, and this is all encapsulated in the memory benchmark. So there are multiple ways to transfer memory using various APIs. There are a lot of memory transfer calls. This benchmark measures how efficient each of those is, and also showcases how to use them efficiently and how to get the best performance out of it. There is also a submission benchmark where we focus on subtle aspect of such things like what is the kernel submission time, what is the completion time, so the time since the kernel ended till the host see that this kernel ended. What are the resource allocation costs, like how fast can you allocate host memory, how fast can you allocate device memory, how fast can you migrate resources. In this benchmark, we also measure what are the thread scheduling costs. If you execute an empty kernel, how much it would take on the GPU to schedule one thread, 1 million threads, 10 million of threads, how efficient GPU is in scheduling of those. So all of those things related to submission are measured in this benchmark. Then we have an overlap benchmark when we run multiple processes sharing one GPU card to see how they execute, if there are any synchronizations, overheads, drawbacks. This benchmark does this. We also have a multi-threaded benchmark where we use one process, but this process uses APIs from multiple threads. So it can be used to see if there are any if there is any contention, if there are like any mutexes, how those API behave when there are multiple threads. So you can easily like change the amount of threads that this benchmark uses. You can see if how increasing the threads, how it influences the execution of the APIs, and so on and so forth. We also have an atomic benchmark where we basically measure how efficient the GPU is with running different atomic operations. There are a lot of atomic operations in the OpenCL standard, especially after transition to 2.0 atomics. There are scopes, there are like different operation types. This is like quite sophisticated. So we have written a benchmark to make sure that all of those are as efficient as possible. And we measure those in various scenarios. We permute by all those types, scopes, and memory orders to make sure that we cover all bases. So this is like a quite humongous test suite with a lot of use cases. We need to be sure that all atomics are efficient. And finally, we have like a kernel benchmark where we can do various operations in the kernel on the GPU itself. So how fast we are doing additions, subtractions, multiplications, everything like that. This is what this benchmark measures. And this is one optimization that I would like to share to showcase that this is already like proving to be useful, and this is already boosting the developer efficiency. So our client came to us that he's using like USM highly in his application, and there's like a lot of SYCLcon as SVM pointer calls because it needs to set all those arguments to the kernel, and there are a lot of pointers. If you have a lot of pointers, then you need to obviously have a lot of kernel arguments. And customer was complaining that even though the resources are not really changing, the SYCLcon arg has a constant like overhead. Even if the same argument is set, the driver is like doing all the thing, all the programming. So this created a performance opportunity to like check in the driver if a given argument is already set, and if so, do not set this logic, because it would pretty much mean that we would program exactly the same thing in the driver, and the kernel state wouldn't actually change because we are setting the same argument on the given kernel. And using the client's workload, it was very challenging to actually optimize this, because this was like only a piece of the application. It was not the whole application. Obviously, setting kernel arguments is not like a substantial part of the application. But in this workload, due to a high amount of those calls, it was creating a severe overhead. So we added a compute benchmark scenario for this. And this, when you think of this optimization, it may sound simple on paper, but there are like some corner cases. And those corner cases are important because with SVM, you can like free the memory, you can call the allocation call once again, and you can get exactly the same pointer. And if you go to like this SYCLcon arg SVM pointer API with the same pointer, well, it's not basically the same allocation. It's you were lucky to get the same pointer, but you need to reprogram the GPU state because it's completely new allocation. So this creates like a complexity for this optimization. And obviously the application from our clients was not doing this, but we needed to be sure that the driver would work after the caching optimization. And with compute benchmarks, it was very easy because we added all those scenarios that are corner cases to the compute benchmarks. So this created an environment in which we have the client scenario in compute benchmarks, which we care and we need to optimize. We have corner cases scenario in which we still need to reprogram the state. And with those two scenarios, we were able to create a driver implementation that covers both of those scenarios and still optimizes the client workload. And it's very important because otherwise, without compute benchmarks, we wouldn't have this second scenario where the application is actually freed and we get the same pointer from the for the subsequent alloc call. So we wouldn't be able to like be sure that optimization works in all cases. And with compute benchmarks and implementation like that, we were sure about this. So that was a very important fact. And this resulted in optimizing 6 times the SYCLcon as being pointer, and the whole workload was boosted by 15%, which is a lot. And what's crucial here is that actually the test itself, the call itself right now takes 50 nanoseconds, which is like very small and tiny times. Basically, the profiling tools are not even capable of catching so small things. So only by writing a dedicated compute benchmark test that measures only this thing, you can easily check the impact of your optimization. So yeah, this is the framework, this is the test, and here will be like some plans and some contribution guidelines if you would like to contribute and use this project. So if you would like to contribute, you need to follow some rules that are fundamental to this project going forward. So test needs to be quick. Like the whole test suite really needs to like run within like seconds, not within minutes. This all needs to be fast. This all test needs to be like quick and small. Another important thing is to not add sophisticated tests measuring multiple things. I would be more than happy to have like 5 separate tests measuring each of those 5 things and having one test measuring 5 things. And the reason for this is if you optimize, you don't want to look at the blobs of multiple cores. You want to isolate your optimizations to a separate thing. This makes things much easier, and this makes optimizations much more successful. Avoid any wrappers, avoid like complicated logic in your tests. Do not obfuscate your code. Make sure that your tests are clean, are easy, simple, and comprehensive. And the reason for this is your tests can further be used as a pattern how to use API efficiently, how to showcase the given code. So the less wrappers you use, the more API, the more plain API you use, the more the test is better to explain to anyone because anyone understands how API works, and wrappers are not like trivial sometimes. Make sure that the test is stable. Make sure that it produces reliable results. Make sure that it's not like having substantial problems in terms of a noise factor. Do not add like any external dependencies. Do not add the requirements for some like additional libraries for some packages. This creates a reproduction problem later when people are using this compute benchmark. And the goal is to simply download and build without like using any external packages. That's why we don't use any external libraries. That's why we don't use any like helpers. We encapsulate all in the repository, so you can quickly get on the bot and run those without the substantial problems of obtaining the dependencies of all those problems that you run when you start having those. Do not require any like additional packages. Pretty much only the driver should be needed to run. Like if you run with OpenCL, make sure to install OpenCL driver, but that's the only package that should be required by the benchmark itself to run it. And look out for the permutations. What we learned is very easy to permute the test to match. So if you permute it to match, you'll create like 10,000 iterations, and the test would be long, and analyzing those permutations would be difficult. So do it wisely. Do it with the common sense. Avoid to like heavily abuse this. And clearly describe what your test does. Like what are the parameters, what they change, what the test is expected to test, what should be the outcome, what test measures, because further users would look at your documentation and they would need to understand it properly without like asking. So this needs to be like verbose, simple, and comprehensive. Okay, so our plan, we use this tool on a daily basis. It greatly improves our efficiency. We do not plan to like move out of it. So we are adding tests on a daily basis to this. Go to our GitHub, try it out, like build it, try to run it on your architecture, see what are the scores. We highly also encourage you to contribute to the project, like add new backends. Like an example, you may add a CUDA backend or something like that. You may add implementations for like OpenCL CPU, add like a CPU backend to the framework, add those capabilities. We are open to contributions. The project is in open source, and anyone can create a pull request and contribute to it. So yeah, having that said, thanks for the opportunity to present at IWOCL. And yeah, go ahead and try. Thanks. Bye-bye.